In question 1, we've got g of x here, and we need to show that g of x is 0 has a root alpha in the interval 3 to 4. So all we need to do here is evaluate g of 3 and g of 4, and we're hoping for a change of sign. So I'm going to go on my calculator, I press 3 and equal, so I'm storing the number 3 on my answer key. Then we've got answer to the power of 6 plus 2 ans minus the 1000 to evaluate g of 3. This gives an answer of minus 265, and I'll do the same thing for g of 4. So all I'm gonna do is press 4 and equal. I've just stored the 4 on my answer key. I press the cursor up to obtain the previous expression. I press the equal sign. I get 3104. So we see that g of 3 is less than 0 and g of 4 is greater than 0. And we therefore conclude that since there's a change of sign and g of x is continuous, then we have a root in the interval 3 to 4. Notice that you need to mention both the change of sign and the continuity of g of x in order to obtain the final mark. In part B, we need to use a given iteration formula with a starting value of 3 to find to 4 decimal places the value of x2, and then by repeated iteration the value of alpha also correct to 4 decimal places. So we will start by using the iteration formula with x1 is 3. So I'm going to go on my calculator, 3 equals, I've just stored the 3 on my answer key, and then I'm going to do the 6th root. So I'm going to put a 6 there, and then 1000 minus 2 ans, and each time I press the equal sign it's another iteration. So we are starting with x1 is 3, so when I press the equal sign I'm going to be obtaining x2. So let's do that. We get 3.1591 correct to 4 decimal places, and if I keep pressing the equal sign, we see that the first few decimal places stabilize, and we can easily conclude that the value of the root alpha is equal to 3.1589 correct to 4 decimal places. In question 2, we've got the graph here showing the linear relationship between log t base 6 and log x base 6, and the straight line passes through 0, 4, and 2, 0. Well, we need to find an equation linking log t with log x, and then find the exact value of capital T when x is 216. Well, let's start by reminding ourselves that the gradient is given by y2 minus y1 over x2 minus x1. Well, in our case, the gradient is 4 minus 0 over 0 minus 2, which gives an answer of negative 2. We can see that the cut on the y-axis is 4, so c is 4, the y-intercept, and therefore we conclude that log of t base 6 is equal to 4 minus 2 log x base 6. Now in II, to find the value of capital T when x is 216, I will simply substitute x with the value of 216 to get the log of t base 6 is 4 minus 2 log of 216 base 6. Well, if I plug this on the calculator, the right hand side gives me the value of negative 2, and therefore we can see that the capital T is equal to 6 to the negative 2, which is 1 over 36. And then in part B, we need to find an equation not involving logs that links t with x. Well, we will start with what we obtained in AI, and the first thing to do is write this as log of t base 6 is equal to 4 minus log of x squared base 6. It's the power law of logarithms. I will then collect all the log expressions on the left hand side to get log of t base 6 plus log of x squared base 6 is equal to 4. And then the product rule of logarithms says that the sum of the logarithms can be written as the log of the product. So I've got log of tx squared base 6 is equal to 4, which means that tx squared is equal to 6 to the power of 4, and therefore tx squared is 1296. Notice that we don't have to make t the subject of the formula. We just need to obtain an equation that links t with x without involving any logs. In 3i, we're asked to find the derivative of ln sine squared 3x, writing our answer in its simplest form. Well, this notation here simply means that if y is ln of sine squared 3x, then we need to find dy dx. So this means that we will start by differentiating the ln, and when we differentiate ln, it's the derivative of the inside over the inside. Well, the derivative of sine squared 3x means we get the power down of 2. We deduct 1 from the power, so it's sine of 3x times the derivative of sine 3x, which is going to be 3 cos of 3x over the inside, which is sine squared 3x. Now we can see that the sine 3x cancels out with the sine squared 3x, leaving a sine 3x in the denominator. So we're looking at 6 cos of 3x over the sine of 3x, which of course simplifies to 6 cot of 3x. In II, we need to find the derivative of 3x squared minus 4 raised to the power of 6. So we will start by getting the power down, 6, deducting 1 from the power, 3x squared minus 4 raised to the power of 5, times the derivative of the bracket, and the derivative of the bracket, the 3x squared minus 4, gives a derivative of 6x, and therefore this can be written as 36x times 3x squared minus 4 raised to the power of 5. And then in part B, we're asked to show that the integral of x times 3x squared minus 4 raised to the power of 5 from 0 up to root 2 is equal to r, where r is an integer to be found. Well, if we look again at the IIA part, we've just seen that the derivative of 3x squared minus 4 raised to the power of 6 is 36x times 3x squared minus 4 raised to the power of 5. And we can see that the structure of the derivative matches what we've got within the integral here. So this means that if we go backwards, then we can see that the integral of 36x 3x squared minus 4 raised to the power of 5 should be 3x squared minus 4 raised to the power of 6. And we've got limits of 0 and root 2. So I will evaluate this integral. We're looking at 3 times root 2 squared minus 4 raised to the power of 6 minus 3 times 0 squared minus 4 raised to the power of 6. So if we plug this on the calculator, we get an answer of minus 4032, which simply means that to find the integral of x times 3x squared minus 4 raised to the power of 5, the only difference is the 36. So I will divide my answer we just obtained by 36. So this should be minus 4032 over 36, which gives an answer of minus 112. In question 4, we've got the function f defined to be 2x squared minus 5 for x being greater than or equal to 0 and being a real number, and we need to state the range of f, where we can start by stating that x squared is greater than or equal to 0 for all x belonging to the real numbers, including x being greater than or equal to 0, which means that 2x squared is greater than or equal to 0, and therefore 2x squared minus 5 is greater than or equal to negative 5. So this means that f of x is greater than or equal to negative 5. The range is the values that we can get as the output, it's the y values. And what I have done, I have started with the expression for x squared and essentially reconstructed f of x to arrive at f of x being greater than or equal to negative 5. In part B, we're asked to sketch y's f inverse, where f of x has already been sketched on this. Well, we know that the graphical relationship between f and f inverse is that one is a reflection of the other along the line y equals to x. So if I draw the line y equals to x, then we can see that any point lying on the mirror line will remain on the mirror line, and the cut on the y-axis will now become a cut on the x-axis, and therefore we expect f inverse to look something like this. In part C, we need to find the exact x-coordinate of P, which is the point of intersection between f of x and f inverse of x, using algebra and showing the working clearly. So if we look back at the diagram, we can see that the point of intersection between f and f inverse is the point here, which also happens to be a point of intersection between f of x and the mirror line y equals to x. So this is the point for which we're trying to determine the x-coordinate. So instead of setting f of x to be equal to f inverse of x, I will simply set f of x to be equal to x. So this means that 2x squared minus 5 is equal to x, and therefore 2x squared minus x minus 5 is equal to 0. Well, I've been told to use algebra, which means I need to show the substitution into the quadratic formula, which means we've got x is equal to negative minus 1 plus minus the negative 1 squared minus 4 times 2 times negative 5 and all square root and divided by 2 times 2. So if we plug this on the calculator, we get that x is 1 plus minus root 41 over 4. However, notice that we're looking for a single point, and looking at the diagram here, we can see that P has a positive x coordinate, and therefore we conclude that x is equal to 1 plus root 41 divided by 4. Now, in case you are wondering what's the 1 minus root 41 over 4 corresponding to, well, if we look at the diagram once more, and if I continue my parabola without the restriction that x is greater than or equal to 0, then the 1 minus root 41 over 4 is that point there, which is of course not part of the function because the domain of the function is defined to be for x being greater than or equal to 0. In 5i, we need to solve for x between 0 and pi. The equation x minus 2 brackets root 3 sec x plus 2 is equal to 0. Well, we know that pi is 3.14, so we're looking for solutions between 0 and 3.14. The equation has already been given in a factorized form, which means that either x minus 2 is equal to 0 or the root 3 sec x plus 2 is equal to 0. So we can easily see that x is 2 is a solution that lies within the range of values here. And then on the right hand side, I've got root 3 sec x is equal to negative 2, and therefore sec x is negative 2 over root 3. Well, we know that sec x is the reciprocal of cos x, so we've got that cos of x is minus root 3 over 2. So I'll find the principal value, which is shift cos of minus root 3 over 2. If you plug this on the calculator, you get a value of 5 pi over 6, and therefore we conclude that x is plus minus the 5 pi over 6 plus 2 pi k. Well, we're between 0 and pi, so we can easily conclude that the only solutions are x is 2 or 5 pi over 6. In II, we need to solve for theta between 0 and 360 degrees. 10 sine theta is equal to 3 cos 2 theta. So the first thing to do is use the double angle formula for cos 2 theta, which leads to 10 sine theta is equal to 3 brackets 1 minus 2 sine square theta. So I'm trying to obtain a quadratic in sine theta. This leads to 10 sine theta is equal to 3 minus 6 sine square theta, and therefore collecting everything on the left hand side will lead to 6 sine square theta plus 10 sine theta minus 3 is equal to 0. I will use the quadratic formula to obtain values for sine theta, and we've got sine of theta is equal to negative 10 plus minus 10 squared minus 4 times 6 times negative 3 and all square root divided by 2 times 6. Now, if you plug this on the calculator, we get that sine of theta is equal to minus 5 plus the root of 43 over 6, which numerically gives a value of 0.2595 ... or alternatively that sine of theta is equal to minus 5 minus the root of 43 over 6, which numerically gives a value of minus 1.926. Immediately we know that this is not okay. It's rejected, it's not valid because sine of theta varies between minus 1 and 1. So I will simply write here reject, it's not valid, and I will proceed with the first value we obtained for sine theta. So the principal value is simply shift sine of 0.2595 ... and this gives an answer of 15.0447 ... and therefore theta is the principal value of 15.0 plus 360k, or alternatively theta is 180 minus the PV plus the 360k. So k is an integer, it could be positive, negative, or 0. I can easily see that since I'm between 0 and 360, the only solutions are for k being equal to 0, and therefore we get the first solution to be theta to be 15.0, and the second solution to be 165.0. In question 6, we've got the graph of f of x, where f of x is 3 modulus of x minus 2 minus 10. The vertex as shown is point P, and we need to find the coordinates of P. Well, we know that the vertex is at the point where the modulus becomes 0. So if we've got x minus 2 being 0, that means that x is 2. So the x coordinate of P is 2. And if x minus 2 is 0, then we can simply see that f of x is negative 10, and therefore the y coordinate of p is negative 10, meaning that the coordinates of p are 2, negative 10. In part B, we're asked to find f of 0, so it's a composite function. So the first thing to do is find f of 0. We do the inside, and then we proceed with the outside. Well, f of 0 will simply be 3 modulus of 0 minus 2 minus 10. So this gives f of negative 4, and I will now substitute again x with negative 4 into f of x. So this is 3 modulus of negative 4 minus 2 minus 10, and this gives an answer of 8. In part C, we need to solve the given inequality, and the first thing to do is go back to the graph given here and identify each of the line segments with their individual equations. Well, on the right hand side, we are looking at y is 3 brackets x minus 2 minus 10. So the modulus is behaving like a normal set of round brackets. So I'm getting y is 3x minus 6 minus 10, which is y is 3x minus 16. Whereas on the left hand side, we've got y is minus 3 brackets x minus 2 minus 10. So this time the modulus behaves like a normal set of round brackets with a negative sign outside. So we get y is minus 3x plus 6 minus 10. So we get y is negative 3x minus 4. Well, the right hand side of the inequality says 5x plus 10. So if we consider the straight line with the equation y is 5x plus 10, then we're looking at the line going uphill, certainly steeper than the line y is 3x minus 16. So we're expecting something like this. Obviously, for 5x plus 10 to be greater than the modulus graph, then we want this part of the curve. So we're interested in the critical value, the point of intersection between the y is minus 3x minus 4 and the y is 5x plus 10. And any value of x to the right of this will be satisfying the given inequality. So I will start by finding the x value of the point of intersection. So minus 3x minus 4 is equal to 5x plus 10. Which means that negative 14 is 8x, so minus 14 over 8 is x, which of course simplifies to minus 7 over 4. Well, any value of x to the right of this will satisfy the given inequality, so we're looking at x being greater than minus 7 over 4. In part D, we're asked to solve the equation f of modulus of x is 0. So looking at the graph of f of x, I will consider what the graph of f of modulus of x looks like and then proceed in solving f of modulus of x is 0. Well, if we're looking at f of modulus of x, then we ignore anything on the left-hand side of the y-axis. So I'm making this dotted, and then anything on the right-hand side, this part here, is reflected on the left-hand side. So we are looking at the points of intersection with the x-axis, the roots of this. So I'm calling these points R and Q. And we have already established that this line here has equation y is 3x minus 16. So we can easily see that at Q, we've got that y is equal to 0. And therefore, we've got 3x minus 16 is 0. And therefore, 3x is 16. Which gives me that x is 16 over 3. And then by symmetry, looking at the graph, this is symmetric about the y-axis. We can easily conclude that at R, we've got that x is equal to minus 16 over 3. So we've got a total of two solutions, the 16 over 3 and the negative 16 over 3. In question 7, we've got a scientist studying two different populations of bacteria. The number capital N of bacteria in the first population is given by capital N is capital A e to the kt. And we are told that had 2,500 bacteria at the start of the study and 10,000 bacteria 8 hours later. Well, we need to determine the exact value of A and the value of K to four significant figures. So let's start with the first piece of information. We have been told that when T is 0, then capital N is equal to 2,500, which means that if I substitute in the given equation, we get 2,500 is equal to A e to the power of 0. And therefore, we conclude that the value of A is 2,500. And then the second piece of information, we are told that when T is 8, then capital N is equal to 10,000. Once more, I will substitute to get 10,000 is equal to A, which we found to be 2,500 e to the 8k. Well, if I divide both sides by 2,500, I arrive at 4 is equal to e to the 8k, and therefore ln of 4 is equal to 8k, which means that 1 over 8 ln 4 is the value of k. Well, we have been told to give k to 4 significant figures, and this gives 0.1733 for the value of k. We're then told that there's a second population where this is modeled through capital N is 60,000 e to the negative 0.6 t, and we need to find the rate of decrease of the bacteria in this population 5 hours after the start of the study. So we need to find an expression for the derivative and evaluate it when t is 5. So starting with the expression for capital N, we need to find dn dt. So this is going to be the 60,000, and then it's times the derivative of the exponent of the exponential term, so the negative 0.6 times e to the minus 0.6 t. Well, this simplifies to minus 36,000 e to the minus 0.6 t, and all we need to do is substitute t is 5 to evaluate the derivative. So dn dt when t is 5 is minus 36,000 e to the minus 0.6 times 5. Well, this gives an answer of minus 1,792.33 ... which means that the rate of decrease correct to 3 significant figure is 1,790 bacteria per hour. Please be careful here, the rate of decrease is not negative, the rate of decrease is positive because the negative is incorporated within the word decrease, and therefore the correct answer would be 1,790 bacteria per hour. Now when t is capital T, the two populations are the same, and we need to find the value of capital T, giving our answer to 3 significant figures. So all I need to do is equate the two expressions for the populations. So we've got 2,500 e to the kt is equal to 60,000 e to the minus 0.6 capital T. Well, notice that I'm just using k, and we know that k was found to be 1 over 8 ln 4. I'm not going to substitute the numerical value of k because it's going to make the whole equation a bit messy. Well, the first thing to do is cross multiply to isolate the exponential term. So we've got e to the k capital T over e to the minus 0.6 capital T is equal to 60,000 over 2,500, and this leads to e to the kt plus 0.6 t is equal to 24. I will take a ln of both sides to arrive at k capital T plus 0.6 capital T is equal to ln of 24. And if I factor out the t on the left hand side, I get capital T brackets k plus 0.6 is equal to ln of 24. And therefore capital T is ln of 24 over k plus 0.6. Remember, we've got the numerical value of k. If I plug this on the calculator, we get t is 4.11 hours. In 8a, we've got the graph of f of x here, where f of x is 2x plus 1 raised to the power of 3 times e to the minus 4x, and we need to find an expression for the derivative f dash of x. Well, here we need to apply the product rule of differentiation. So we are starting by differentiating the first, which is 2x plus 1 raised to the power of 3. Well, the derivative of this is get the power down of 3 times 2x plus 1 raised to the power of 2 times the derivative of the inside, which is 2, and I keep the second, e to the minus 4x, plus I keep the first of 2x plus 1 raised to the power of 3, and I differentiate the second, e to the minus 4x, which is giving me a derivative of minus 4 e to the minus 4x. Well, notice that there is a common factor of 2 brackets 2x plus 1 raised to the power of 2 times e to the minus 4x, which is leaving me with a 3 here, minus a 2 times 2x plus 1, and therefore I only need to simplify the final set of brackets here. So we're looking at 2 brackets 2x plus 1 raised to the power of 2 times e to the minus 4x, and in brackets we've got 3 minus 4x minus 2, and therefore we've got 2 brackets 2x plus 1 raised to the power of 2 e to the minus 4x 1 minus 4x, which matches exactly what we have here, which means we can safely conclude that the capital A is equal to 2. In part B, we are asked to find the exact coordinates of the two stationary points on C. Well, we know that stationary points satisfy f dash of x is equal to 0, and we just obtained an expression for f dash of x, so we need to solve this being equal to 0. Now we can see that either 2x plus 1 is equal to 0, or the 1 minus 4x is equal to 0, or alternatively the e to the minus 4x is equal to 0. Well, for the 2x plus 1 is 0, we've got 2x is equal to negative 1, and therefore x is minus a half. I will proceed in finding the corresponding y coordinate, so it's going to be y is equal to 2 times minus a half plus 1 close brackets raised to the power of 3 times e to the negative 4 times minus a half. Well, if you put this on the calculator, you simply get a 0 because the first bracket here is simply 0. Now for the 1 minus 4x is 0, we get 1 is equal to 4x, and therefore x is a quarter, and I will proceed in finding the corresponding y coordinate. We've got y is equal to 2 times a quarter plus 1 raised to the power of 3 times e to the minus 4 times a quarter. So the bracket here raised to the power of 3 is giving me 27 over 8, and the e to the minus 4 times a quarter is e to the minus 1. So that's the y coordinate of the second stationary point. And for the e to the minus 4x being equal to 0, we know that this is not yielding any solutions. It's rejected, it's not valid, because e to any number, e to any power will always give me a positive result. And therefore we conclude that we've got two stationary points, the minus a half, 0 being the first one, and the second one being a quarter, 27 over 8 e to the minus 1. In part C, we're told that g of x is a times f of x minus 2, and we need to find the coordinates of the maximum stationary point on the curve with equation y is g of x. Well, if I first briefly go back to the graph of f of x given here, we can see that the maximum point is here. It's the point which has a positive x coordinate, and therefore, according to the results of part B, it's the point with coordinates a quarter, 27 over 8 e to the minus 1. Well, here we're dealing with two transformations. We've got the f of x minus 2, which simply means we are adding 2 to x, and we've got the 8 outside, which simply means we need to multiply y by 8. So if I take the original stationary maximum point on f of x, which was a quarter, 27 over 8 e to the minus 1, we know that this will take me to an x coordinate. If I add 2, I go to 9 over 4. And if I multiply the y coordinate by 8, I get 27 e to the minus 1. In 9a, we need to show that cos of 2x over sine x plus sine 2x over cos x is equivalent to cosec x. So we need to prove the given identity. I will start from the left-hand side, and I will express everything over the same denominator. So we're looking at cos of 2x times cos of x plus sine 2x times sine x, and all of it over the sine x times cos x. We're looking at the numerator. We should be able to recognize this as the addition formula for cos of a minus b, and in our case this is cos of 2x minus x over the sine x cos x. So we can simply see that the numerator is cos of x and the denominator remains as sine x cos x. Well, obviously the cos x will cancel out, and the 1 over sine x is simply the cosec x, which is the right hand side as required. In B, we are told hence solve for theta between 0 and pi over 2 the given trigonometric equation here, giving our answers to 3 significant figures where appropriate. Well, we should be able to recognize these as simply the cosec theta. So the left hand side of the given equation is cosec squared theta, and this is equal to 6 cot theta minus 4. Well, we know that cosec squared is 1 plus cot squared theta, so this is eventually leading towards a quadratic in cot theta. I will be collecting everything on the left hand side to get cot squared theta minus 6 cot theta plus 5 is equal to 0, which factorizes into cot of theta minus 1 times cot of theta minus 5, and this is equal to 0. So either cot of theta minus 1 is 0, or alternatively we've got that cot of theta minus 5 is equal to 0. So we've got cot theta is 1. And if I take reciprocals of both sides, I get tan theta is 1. Well, the PV for this case is simply shift tan of 1, which is pi over 4, which means that theta is equal to the PV of pi over 4 plus pi k, whereas for cot theta minus 5 is 0, we've got cot theta is equal to 5, and therefore tan theta is a fifth. I will find the PV by doing shift tan of a fifth. This is giving an answer of 0.1974, and therefore theta in this case is the PV of 0.1974 plus pi k. Remember that the k could be any integer, positive, 0, or negative. If I put k to be 0, I get an answer of 0.197 and pi over 4, and these are the only two solutions within the range of 0 to pi over 2. In part C, we need to use the result from part A or otherwise to find the exact value of the given integral here. So starting with the given integral, we recognize that this is simply the cosec x. So we're dealing with the integral from pi over 6 up to pi over 4 of cosec x times cot x dx. Well, this is a standard integral. It integrates to negative cosec x, and we are between pi over 6 and pi over 4. Well, I will substitute the upper limit, so we've got minus cosec of pi over 4 minus the negative cosec of pi over 6. Well, the minus cosec of pi over 4 is simply minus root 2, and the negative cosec of pi over 6 is negative 2, so minus negative 2. So this is giving me an answer of 2 minus root 2. In question 10, we've got a sketch of the curve with a given equation here, and we need to find dx dy, giving our answer as a fully simplified fraction. Well, I need to apply the quotient rule of differentiation here to obtain an expression for dx dy. So we start by differentiating the top, which is 4y, and we keep the bottom of 3y minus 3, minus we keep the top of 2y squared plus 6, and we differentiate the bottom, which gives me 3, and all of it over the bottom square, the 3y minus 3 all squared. And I will proceed by expanding the numerator and collecting like terms. This is giving me 12y squared minus 12y minus 6y squared minus 18. And in the denominator, I can write this as 3 squared times y minus 1 squared. And this leads to the numerator being 6y squared minus 12y minus 18 over 9 brackets the y minus 1 squared. Well, we can see that there is a common factor of 6 in the numerator, so we're looking at 6 brackets y squared minus 2y minus 3 over the 9 times y minus 1 squared. Well, obviously the 6 with the 9 simplify to leave me a 2 and a 3 respectively, which means that we obtain the final expression to be 2. We factorize the y squared minus 2y minus 3 to give me y minus 3 times y plus 1. And in the denominator, we're looking at 3 brackets y minus 1 squared. This is my final answer. If you didn't factorize the numerator at the very end, that's also acceptable. In part B, we need to use the answer to part A to find the equations of the tangents at the points P and Q, which are points on the curve at which the tangents are parallel to the y-axis. So if we look at the graph, these are the points P and Q, and we're trying to determine the equations of these tangents. Well, obviously, we are looking at lines which are vertical. They are parallel to the y-axis, so they must be of the form x is equal to a number. So looking at what we obtained in part A, that's the expression for dx dy. Well, to find the expression for dy dx, I will simply take the reciprocal of the right-hand side, which is 3 brackets y minus 1 squared over the 2 times y minus 3 times y plus 1. And we do know that if a tangent is parallel to the y-axis, then the gradient is undefined. And looking at the expression for dy dx, we can see that the gradient is undefined when the denominator is 0. So we either have that y minus 3 is equal to 0, or that y plus 1 is equal to 0. So we're looking at y is equal to 3 or y is negative 1. Now for y is equal to 3, I'll go back to the expression for x to find the corresponding value of x. So x is equal to 2 times 3 squared plus 6 over 3 times 3 minus 3. This is giving an answer of x is equal to 4. And for y is negative 1, we've got x is equal to 2 times negative 1 squared plus 6 over the 3 times the negative 1 minus 3, which is giving an answer of x is minus 4 over 3. So if we look at the graph here, the tangent at P has equation x is minus 4 over 3, and the tangent at Q has equation x is 4, and that's the final answer.